applying linear functions. In this lesson, we're going to figure out how to apply linear functions in what they call real-world situations. In other words, using word problems. So, a sporting goods store sells cans of tennis balls. There are 3 tennis balls in each of the cans. The coach of the tennis team is buying supplies. They want you to write a linear function that relates the number of cans to the total number of tennis balls. Graph the function that models this situation. So at this point, what we're looking for is how many. So as we look at this, we want to mark up the text, just like you would learn in your English class. They want you to write a linear function. So we're going to be writing a linear function, and we want to relate the number of cans to the total number of tennis balls. So as we think about that, we have to first define our variables. So we're going to say maybe C is the number of cans. And then we're going to say maybe T is the total number of tennis balls. And so when we write that, we also need to understand that there are 3 tennis balls in each can. So what we want to figure out is how many total tennis balls would we have? So we're going to write T equals, and it doesn't matter what variables you choose. It's really up to you. You do need to define them when you are writing equations from a real world kind of a problem. So if it involves words, you probably need to define those variables. Looking at that, T, there are 3 tennis balls in each of those cans. So that means that we're going to take 3 times each can. So the equation there is going to be T equals 3C. Now we're also going to talk about discrete and continuous data. Discrete data means that you're not going to connect the points because they're not going to have half of the tennis balls in this situation. You're going to have whole cans, and so in this situation you're not actually going to connect the dots. Continuous means that you are going to connect the dots. That would be things like buying gas at a station, something that would continuously flow. Another discrete thing which you would not connect would be like buying nuts and bolts. So in this situation, the other thing we're not going to talk about are negative values because we can't have negative tennis balls or negative cans of tennis balls. So we're only going to use the first quadrant. When you write this, you want to make sure that you label your axes. You want to create your graph. You need to go up by the same amount. It doesn't matter if you go up by the same amount on the x-axis and the y-axis. They don't have to be equivalent. But you do want to go up by the same amount on the x-axis. So you have to have a scale. You also want to label your graphs. At this point, the labeling for this would be number of cans. Or I'm just going to put cans down below. The y-axis, I'm actually going to have that one go up by 3s. And this is just to show you that you don't have to go up by the same amount. You may. This is going to actually be tennis balls. And then we're going to graph these points. One of the things that we know, in this case, this has a +0 on it. So that means that it goes through at the y-axis at 0. There is nothing added or subtracted to our equation. Now 3c means that that's our slope. So we go up 3 units, in this case just up 1 space because it is 3 units long, and to the right 1 unit. Or another way to look at that is for every 1 can, there are 3 tennis balls. So for 2 cans, we would have 6. For 3 cans, 9, so on and so forth. And in this case, because it is not, you can't have a half a can, you're not going to connect these dots. So again, this is a discrete equation. Now here's an example. We're just going to talk about this a little bit. we're going to analyze this. Students in the ninth grade class drew the following graph to represent how much money would be in the class fund after washing cars at a fundraiser. Again, you can't wash half a car and get half the money, so it's discrete again, which means disconnected. In this case, they're saying, what does the slope and the y-intercept of the graph mean for the given situation? So as you're looking at this, we have cars washed here and the balance in the fund here. The slope is going to talk about how far we're going up versus how far we're going over. So in each situation, and it's hard to tell, but it's actually going up $3. And so the slope is 3, which means for each car, we are actually charging $3. The y-intercept, that's this right here where it crosses that y-axis. And what that is, that tells us what we started with in our fund. So we actually started with $25 in our fund, and for each car that we washed, we made $3. So it continuously goes up by 3. Now, if the graph had the same slope but a y-intercept of 15, what can you conclude? Well, what that would end up doing is dropping this whole graph down about $10. So what it would mean is that we'd actually start at $15. It would still have the same slope. We would still charge the same amount, but our fund would be about $10 less because we started at $15 instead of $25. Now, if the graph had a slope of $5, what could you conclude? Well, what that means is that it now would be going up 5 and over for one car. In other words, we started charging $5 per car. So in this case, suppose you drew the following graph to represent how far you ride your bike at a steady rate. What is your rate? In other words, you want to figure out, well, how far did you go? I can see this whole graph goes over 1 hour. You can see the time is in hours. And the miles, if I start at 0, 0, which should make sense if I haven't gone anywhere and no time has passed, I've gone 0 miles. And after 1 hour, I have now gone 12 miles. So my rate, if you wanted to put in the slope triangle, you can. The rate went up 12 units and over 1 hour. So that slope, or my rate, would end up being 12 miles per hour. And that's what that means in this situation. Now, if the graph had a slope of 10, what can you conclude about your bike ride? It means that I would have to go slower. So if I had a slope of 10, and again, remember that rates and slope are the same thing. So rate of change and slope are equivalent. If I had a slope of 10, that meant that I went actually 2 miles per hour slower. So it would actually come down a little bit less. And it would look something like that. So I would conclude that I actually went a little bit slower in that situation. Now at this point, this problem is problem number 6. It is a problem that you will actually see in your homework, so you definitely want to write this down to get ahead in your homework. It says, suppose an elevator is 400 feet above ground. So get an idea, you've got this building, and you've got an elevator inside, and it is 400 feet above ground. After 15 seconds, okay, it is descended to 250 feet. So in 15 seconds, it went down. So here's kind of how you want to look at it. At 0 seconds, we were at 400. This is kind of like a point. And 15 seconds later, we were now at 250. So the question is, all right, write a linear function for the height of the elevator as a function of time. So again, we have t and height. We've got h and t. So h of t is going to equal some value. Now we started off at 400, so that's our y-intercept or our slope, and it's going to descend. So we're going to subtract something. We've got to figure out, well, how far are we subtracting? So we need to figure out the slope. In this case, we want to figure out, well, we went 400 down to 250. So we're going to subtract that, 400 minus 250. And we went from 0 to 15. So 0 minus 15. In this case, 400 minus 250 is going to give us 150. 0 minus 15 is negative 15, which means that our slope is a negative 10 feet per second. So when we write that, it's going to be minus 10t. So our equation h of t equals 400 minus 10t. Now, as we look through this, we have to graph it. Okay? So I'm actually going to erase this slope. Okay. Sorry if you needed that. And now we're going to draw our graph. And when we graph this, again, I don't think we're going to go below ground. We could if we had basements, but I'm just going to actually keep it all positive. Noticing that we started at 400, I'm actually going to go up by hundredths. So our height, is the y-axis, and time is going to be below, and I'm going to actually put that in increments of 10. When you draw a linear function, you really only need to draw 2 points and then draw a straight line through them if it is continuous. Since the elevator will continuously go down foot by foot, it is a continuous graph. So we're going to start this graph at 0, 400. And we have another point at 15, 250, which should approximately be halfway there. And you do want to draw a better graph than what I've got going on here, so that you can actually see where it crosses that x-axis. But you can see the y-intercept, which is a positive 400, and the slope being negative is going down 10 feet per second. Now, is it reasonable to include negative numbers in the range? If you talked about going underground, or if you had basements, or and some of these buildings do go underground, and so that could be a possibility in the negatives. So it is possible, it is reasonable to have negative ranges if a basement is included.